Hello, this video is entitled Entropy in a Nutshell. Dr. Ryan Hayes here from Andrews University in our general chemistry program. We need to learn some things about entropy, very important for predicting whether chemical reactions will go or not. And so today, our topic is this thermodynamic force, another force that we need to think about. It's given the symbol of S, and it's really a description of how energy is dispersed, how it's spread out in a chemical reaction. So things that have positive entropy are going to happen, or entropy is going to make happen. They're going to spread out. So we want to think about that. So we're taking a system that's concentrated. Maybe all the atoms are together, and then as the atoms spread out, we can disperse energy. And this is going to be behind a spontaneous chemical reaction. What's a spontaneous chemical reaction? That is going to be covered in more detail when we talk about Gibbs free energy coming up in another talk. But we need to understand this particular aspect of chemical reactions called entropy. And it's based on the second law of thermodynamics that states that a spontaneous chemical reaction, which is one that takes place, is the result of an increase in entropy in the universe. Things are spreading out. This is behind the second law here. So in our minds, we have this force then that we want to think about and to represent when molecules are spreading out. So if the energy is in a few molecules, then entropy pushes it out to spread out, kind of like these billiard balls here. As the cue ball hits them, they spread out, the molecules spreading out. So maybe entropy is like that white ball as it's hitting the rest of them. So it's more probable, more likely to have a spread out system than it is to have one that comes together. So this is a force. So I think of entropy as this pushing force that's taking chemicals and wanting to spread out. So here's an example. Take water, two waters, and they can split apart into hydrogen and oxygen. Usually you got to put some energy in to make that happen. And as it spreads out, it makes two molecules of hydrogen and one molecule of oxygen. So that's three molecules that it makes in the product stage. So entropy says, yes, that's good. I'm going to push that. I'm going to make that happen. So to go the other way would be then a negative entropy. Entropy is going to resist two hydrogen molecules and one oxygen molecule coming together and make water. So the reverse reaction, entropy, is not going to be favoring that. So in order to understand this in more details, though, we need to kind of think about what's called microstates. It's really just all the different ways you can find a molecule. It can move. We call that translational positions, a translational microstate. They can twist. They can turn in molecules. Those are each angle that a molecule can have as a microstate. How they vibrate, each vibrational position is a microstate, and even the electrons within the atoms and the molecules there and the molecular orbitals, those are also microstates. Why do we need to know that? Well, because entropy wants to favor those molecules that have lots of microstates in them. So going from a simple atom into a more complex molecule, we'd say entropy would favor the system that has more microstates. So we can increase the microstates. Entropy has a greater way to disperse and push into this direction. So we can't have a static view of molecules. We got to have this more dynamic picture here of bonds moving and vibrating, twisting and spinning around and running around with great energy. So all these different systems there are microstates. The other aspect that we need to think about is probability. Probability plays a role in entropy. Probability is weird because that's like a mathematical concept. What would that have to do here? An example of what's called a sort of an experiment, a thought experiment with no enthalpy or anything behind it is this gas on one side of a container. So we have this brown gas here, and on the other side is just the evacuated chamber. There's no gas. We are able to pull a vacuum on there and it's connected with a valve. Well, if you were to open this up, the volume would greatly increase for this gas, maybe double, and that would give the molecules more places to go. So greater volume, the greater the entropy, and the entropy is going to push and make that happen. Well, how does this relate to probability? Well, if you were to take a flask that had 4 gas molecules, we'll call them A, B, C, D, and if they're all on one side, we would say that's, in our thought experiment, like 1 microstate. But if we were to move one of them over to the other side, we could move A, B, C, or D, and that would give us 4 different ways of configuring 3 on one side and 4 on another. I would say that's 4 microstates. Imagine 2 and 2. Well, which 2 would you move over? Well, it could be A and B, B and C, A and D, and all. Well, it turns out there's 6 combinations that you could come up with, 6 microstates. And you can see the other ones. They're 1 and 3. There's 4 opportunities for that. And if they're all A, B, C, D molecules are on the right-hand side, 1 microstate there. Why that's important? Because the more microstates, that's a greater probability. So entropy would actually then push towards the state. If you started on one side, then it was going to push to this side of the chemical reaction where there's a greater dispersion. So it's like it's pushing towards the most probable state. It's like mathematics is a force. I'm sure a lot of mathematicians would say that anyway. But we actually see that in chemistry. So where do we see that with actual chemicals? One of the ways we see it is with phase changes. You see, going from a solid to a liquid to a gas, we find that the position of the atoms next to each other greatly expands and increases, and there's more movement allowed as you go from a solid to a liquid to a gas. We can actually start assigning numbers to these things. Solids have very little entropy to them, and as you go to a liquid to a gas, the entropy increases. So we have a greater way to disperse the energy over a gas. These molecules are moving, they're experiencing a lot of different microstates, and so we can see that they have more entropy. All right, not only does the different phases have different amounts of entropy associated with them, so does molecules at different temperatures. So if you've at a higher temperature, there's more ways to disperse the energy because the molecules can experience different geometries now. They're going to have greater energy because of the temperature to experience different motions, more microstates. And so the increase in temperature is going to increase the entropy of the system. If molecules become more complex, this is another way. Going from methane to ethane to propane, these molecules are becoming more complex. There's more atoms there. There's more microstates. There's more ways to spread out. I have a little video here.
In general, the more complex a molecule, the greater its entropy. We can see this trend by comparing 3 alkane molecules. The amount of motion for each molecule translates into entropy. The more motion overall, the greater the entropy.
All right, so this is great. So one way to simplify it actually, just say, hey, there's more atoms, that means more molecular weight. More molecular weight means more microstates and increase in entropy. But what if the systems that we're looking at all have about the same molar mass? Then we can't use that process. But we can use the number of atoms that are involved in that molecule to help us understand the difference in entropy of these different chemical substances. Going from argon to carbon dioxide, you're going from 1 atom to 3 different atoms. There is an increase in entropy there from our actual measurements that have been done. Propane, which has 11 different atoms involved in it, has even a greater entropy, even though the molar masses are all the same. So I would say molar mass is like a primary way to looking at differences in entropy, and then look at the number of atoms secondly. So more atoms, more entropy in the system. What about solids, ionic solids? Well, depends on the Coulomb's force. Stronger the Coulomb's force, then the tighter the solid, less ways to disperse energy. So magnesium oxide, which has a +2 and a -2, very small atoms, Coulomb's force is very strong, and so it's going to have a smaller entropy than something like sodium fluoride, which has they have less charges, so they're going to be more loosely held together. So they're going to be able to, they're going to be further apart than they would than the distances in magnesium oxide. So if we can increase the bond energy, we're going to decrease the entropy and vice versa. Now, if things are spreading out, like if you're dissolving or making an aqueous system, then that is also going to increase the entropy. So dissolving, just what we learned in chapter 15 about things being dissolved. Could be mixing, creating a homogeneous solution from two things or more that are being mixed together. So this increases entropy. So I'm going to ask some questions right here, and you can pause the video and see if you can answer, it's really A or B for each of these 5 examples. All right, hopefully you got a chance to look at those. Now, if you're evaporating alcohol, it's going from the liquid to the gas phase. This is spreading out. This is a positive entropy. Freezing in water is taking liquid, making it a solid. So this is the contraction of a liquid. So this is negative. Compressing an ideal gas at a constant temperature, you're compressing, you're combining them. That's definitely negative. Heating an ideal gas at a constant temperature gives those molecules more ways to move. And so this increases the entropy. Dissolving is spreading out. So that's definitely a positive entropy. These things can be enumerated, that is put in to numbers. And you can take a look at the solids that are there and different gases and liquids and get a relative idea of the calculatable values that go with entropy. And you can see the units joule per Kelvin per mole, where moles and Kelvin are in the denominator. And we can actually calculate delta S for the system by using this formula here. This is the summation sign. If you sum up all the entropies of the products and you subtract it off from all of the entropies of the reactants, don't forget to multiply by the number of moles that you have in the chemical reaction, the stoichiometric coefficients there. And this is very similar to what we did with enthalpy. So here's an example of one. So let's practice. Let's consider hydrogen and oxygen combining to make water. This is a balanced chemical reaction going from gases to liquid. Here is the representation of this formula. We're going to go find the entropy of water as a liquid, subtract off hydrogen, oxygen as gases. Notice the 2's here correspond to the stoichiometric coefficients. So I plug in the numbers from the table and I multiply them by the number of moles that are there, and the moles will cancel out. And I get a negative 326.9 joules per Kelvin. This is quite a bit of negative entropy. Some may be asking, do I have to memorize all these numbers? No, just be able to look them up. Could we have predicted the sign ahead of time? Remember, this is the reverse of what I was looking at earlier. So entropy is actually resisting this because it wants to spread out to go from 2 moles to 3, not 3 to 2. So we have that going on, but we also have this 3 moles of gas becoming a liquid. So gases are becoming a liquid. This is not favored by entropy. So we got those 2 things, 3 moles of reactants reducing to 2 moles of products, and the confining. So this is not good. Let's just see what happens to this calculation if we left them all as gases, even our product water right here. Does that change the calculation at all? Well, the answer is absolutely, because the gas is a very spread out thing. Here's the formula again. We can go and grab those numbers and plug them in. And so the big thing that changes here is the entropy of water. It's a much bigger number now. So the difference isn't as great when we do the final calculation. Negative 89.1. So entropy isn't as negative now because we're not confining it into the liquid. And so, but it's still negative because of the 3 moles going to 2. All right, so now we've learned a lot about entropy. It's this force that wants to just push and spread things out. We use the symbol S, sometimes with a subscript SYS for system. Most of the time we're just going to call it S, maybe even delta S, especially with the chemical reaction. This is not related to enthalpy at all. So this is the hard part for students as they're learning, is that they think there's a connection, but there's not. And we also lastly learned that there is a way to calculate entropy. Hopefully you now know a little bit more about entropy.